Hello, welcome to Module 1 of Lecture 2 of the course VLSI Design, Verification and Test. In Lecture 1, we went through a bird's eye view of the full VLSI design process. We saw that there are three important levels of abstraction through which the design goes through: the architectural level, the logic level and the geometric level. And we saw different views through which the design goes through as well. So we saw the behavioral view, the structural view and the physical view. And we saw that the design goes through steps which are known as synthesis. We saw a few important synthesis steps: architectural synthesis, logic synthesis and geometrical synthesis or physical design. And now today what we will do is that we will take a more detailed look into the first important design step, that is architectural synthesis or high-level synthesis. So before going into this step, let us say that the initial design starts even earlier than this. The initial design, which we may say as the application level, will also contain a specification of the entire application. Now, this application will also be designed in terms of a set of processes which will be communicating. However, for all of these, if we look from the perspective of an entire embedded system, all these processes we may not need to implement them in hardware. Some of them it will be sufficient for us to implement in software, which means that for those processes, for those blocks of code, we will only use a general purpose processor and execute a high-level program like a C language program for that process and run it, and that will be sufficient. So this step is called hardware-software partitioning. Now the future steps, starting from the architectural synthesis which we are concerned with here, will be concerned with only the hardware synthesis part. So the software will be taken care by a different process, different flow, which we will not take here. So the hardware also, at the beginning of the architectural synthesis step, we will have a set of concurrent communicating processes. Each such process will be described formally using a programming language, a high-level hardware description language program in Verilog, VHDL, etc. And the high-level synthesis step will take it from the architectural level design and will end up into a register transfer level design. So what we will start with: first the Verilog and VHDL description will be there. Then the design analyzer, which is again a program, will transform this program into its control and data flow graph. Given this control and data flow graph, we will perform scheduling, allocation and binding on them and ultimately obtain a controller and a data path. So architectural synthesis is also called high-level synthesis. The input behavioral model is abstracted as threaded concurrent communicating processes. So these processes represent the operations and the data and how the data is transformed through these operations. And process modules have interfaces to other blocks and the outside world, as we said yesterday. And the output of the high-level synthesis step is a data path and control path. The data path is composed of a set of registers or a register bank, a functional unit bank, and interconnection network. So this is the register bank. This one is the functional unit. This one is the functional unit bank. This is the interconnection network. Okay, and along with that we will have this controller FSM, which will control operations, the flow of data in this data path. So yesterday we said that registers are connected to functional units via muxes. The functional units again are connected to the registers through demuxes. mux and demuxes are controlled by the FSM controller, and after this design process, after the high level synthesis process, the design gets broken down into a set of steps, into a set of clock steps, and at each step some registers and functional units are activated, and these activations define the RTL assignments. So we also said yesterday that we will have a set of parallel register transfers like R1 equals to R2 into R3 and R4 equals to R2 into R2 plus R3 in time step 1, and in time step 2 we have R2 equals to R3 plus R4 and R5 equals to R6 minus R1. So although I said this yesterday, but I did not possibly take a concrete example showing the use of these muxes, demuxes, etc. So I'll just go through yesterday's example again once more and show you where the muxes and demuxes are before proceeding further. So I said yesterday that I have a basic block. This is a basic block, and corresponding to this basic block, let us say we have arrived at a schedule, and in this schedule we said that the first statement in the first statement we said E equals to A plus B. So it happens in time step 1. This has two time steps. This has two time steps. In time step 1, what happens? A and B are added and E is produced, and in time step 2, this A and E are added. The second statement occurs, A and E are added and G is produced. This cannot be done in time step 1 because E is dependent, because the E is on the right hand side in statement 2 and is only defined, that is on the LHS of it is in the LHS of statement 1. Similarly on the other part, and we said that to implement the schedule, so we will do an allocation and binding. So first of all, we have four registers R1, R2, R3 and R4, in which I have A, B, C and D. And then what happens is that what we have decided is that after time step 1, at time step 1, A and B, these two should be activated. These two should be activated, and then the output will go to R2 and not to R1. For R3 and R4, similarly it will happen. So what we will just take an example now. So what we said is that initially we have four registers. This was R1, R2, R3 and R4. Okay, and we said that a mux will control which of the registered inputs should go to a functional unit. Okay, and what we have is a situation like this. And initially I have this A, B, C and D in these four registers, and this mux has this mux one has select inputs is 0, S1 of say 1, S01, S1, 1, and this one similarly has these four inputs from these four registers similarly. Okay, these four registers similarly, and will also be similarly controlled by two select inputs, say S02 and S12. Okay. And the output, as I said, will contain a demux. Will contain a demux, which will decide the output of the adder should go to which particular okay. So this will also have two select inputs, say S03 and S13, right? So now what should be the set of control signals that we should have? If you want, let us say, the E output to be here and the G output to be here, say. And for C, let us say we have C and D, and let us say we want this C and H, C and D, C and D to be here, and the final output H to be here. If this is so, then what should be the register transfers what should be the values of these select inputs? So at T1, say, what should be the select inputs? I want to select what for mux 1, for the adder 1. What do I want? Similarly, this will again, I have not drawn the other part, there will be an adder 2 here, which will again have these 2 inputs and 2 muxes and 1 demux for it, that I have not shown. That I have not shown. But let us say for adder 1, what will happen? Is 01, what? Let us say this is I0, I1, I2, I3. So R1 will be selected when mux 1 is for all when select inputs are 0, 0. So R1 will be selected when select inputs are, say, 0, 0. Here I want to select for mux 2, I want to select what? For mux 2 I want to select R2, and that will be selected when it is 0, 1. So S20 equals to 0 and S12 equals to S12 equals to 1, right? So then what will happen in the first time step? I will be able to select R1 and R2. For mux 1 will select R1, mux 2 will select R2 at the first time step, and hence adder 1, if it is activated in time step 1, will get the correct inputs A and B. Then what will happen? At time step 1, the output should go to where? Should go to R2. So therefore, the demux should also select S03 equals to 0 and S13 equals to 1. So why? Because if it selects if it selects this select inputs, the output of the adder will go so this particular line which goes to R2 will be selected, and the output E will get stored into R2 as desired. So similarly, I will be able to, therefore in time step 1 I will be able to activate the register transfer R2 equals to R1 plus R2 for using these control signals, right? So similarly, I will be able to get the set of register transfers through proper control signals by appropriately selecting the select inputs of these muxes and demuxes. I will be able to appropriately select control signal so that the appropriate register transfers are activated. Okay, so with this example, we now go and look at the overall high-level synthesis steps. So with this we come to the end of module 1 of lecture 2.